Laplace transform from my book Tensor Calculus in the Theory of Relativity. Laplace transform converts a positive real variable function f of t, which is in time domain, into a complex variable function, capital letter F of s, of complex frequency domain or S domain. It is used to solve and simplify differential equations, such as converting a linear differential equation into an algebraic equation, whereby f of t is defined for t being equal or greater than 0, and by integration with respect to t, it vanishes and we left up with s. E to the minus st is the exponential decay factor, and s is a complex number, and the capital letter f of s is the transformed function of frequency domain. The magnitude of the complex number is represented by the length of the arrow over time. S is the addition of a real part, alpha, and the imaginary part, phase, multiplied by I, the imaginary number. As alpha increases, the magnitude will increase rapidly, and if alpha is equal to 0, the magnitude remains constant. As the phase increases, the arrow will rotate faster. The alpha and W, which is the phase, are the points of complex plane. Let us now come over the existing theorem of Laplace transform. The Laplace transform exists or converges if it follows the two conditions. F of t is a piecewise continuous on the interval 0 to plus infinity. This means that f of t has a finite number of discontinuities in a finite number interval, from 0 to t final. Moreover, f of t is of exponential order, where there exists a constant m greater than 0 and a constant c, such that the magnitude of f of t must be less than or equal to m multiplied by e to ct, for t being greater than the t final. Thus, f of t is bounded by an exponential growth, as it can grow faster than the e to the power st, such that s is greater than 0 as t approaches infinity. Summing all that, for every s greater than the constant c, the Laplace transform exists. And now, some properties concerning the Laplace transform. Property number 1. Linearity. The Laplace transform of a linear combination remains the same linear combination of the transform of the functions f of t and g of t, where a and b are constants. Property number 2. Time shifting. By delaying the function f of t by t0, the Laplace transform will be multiplied by e to minus st0, showing how f of t behaves when the function is delayed. The Laplace of ft minus t0 must be multiplied by the unit step function gamma of t, such that for gamma of t equal to 0, the time is less than 0, and for gamma of t equal to 1, time is equal or greater than 0. The third property is frequency shifting. By multiplying the function f of t by an exponential factor, it shifts the Laplace transform, the capital letter f of s, by a in the complex plane, thus shifting from a frequency domain to a translation in S domain. Last but not least, differentiation. The Laplace transform, or the first derivative of f of t, is expressed by this equation, where the initial value theorem states that the limit as s approaches infinity of s multiplied by the capital letter f of s is equal to f of 0 plus. However, the Laplace transform of higher order derivative, or the second order, can be extended from the first differential or the first derivative of f of t. These are basically the most important properties for a Laplace transform.